Okay, so continuing on here with the idea of multiple comparisons, moving from linear contrast to looking at, actually instead of one contrast, looking at several contrasts. So suppose we're back in the problem with the three additives, the fuel additives, and suppose we want to test three hypotheses. So something that would look like this. Actually, not the additives problem, but the location problem. Selling price as a function of location. Suppose we wanted to compare mu1 and mu3. So that would be, I believe that is bayfront and oceanfront. Suppose we also wanted to compare the average of mu1 and mu3 to the average of mu2 and mu4, and we did that with the previous linear contrast. And can I say and again? And another hypothesis, suppose we wanted to compare mu2 to mu3, so this would be bayside to ocean front. All right, and so we have three hypotheses that we want to compare. We could create a contrast for each of these three, and for each of them we could do the F-test as specified above. Now, if we do that, each of the contrast is tested, suppose, at the same value of alpha, significance level. We're going to denote that as alpha I. Okay, the individual comparison type 1 error rate. That's what we've got here. That's an important idea for us. Thus, we have an alpha I chance of making a type 1 error on each of the M test. All right. Now, actually, I'm going to try to, let me pause this real quick. Okay, so I paused it real quick anyway to get this pen working the way it should. We also need to consider the probability of falsely rejecting at least one of the M null hypotheses. So in this example here, where there's three null hypotheses that we could test, what is the probability that at least one is falsely rejected? Now that's different than looking at a per test basis. This type 1 error rate is called the experiment-wise error rate. Okay, and we're going to call this alpha with a subscript E. The value of alpha E takes into account that we're looking at several tests, each having an alpha I chance of making a type 1 error. Now it turns out that if MSW has an infinite degrees of freedom so that the tests are independent, this is actually a fictitious, it's a place where we're really not ever going to be in this class. But if that was the case, then there's this relationship between alpha E and alpha I, and it's given by this mathematical expression here. In your book, studies alpha E for a fixed alpha I as the number of tests increase. And so I'm going to reference here the book. Table 9.5 has that. Notice if you look there, alpha I is either 0.1 or 0.05 or 0.01, and then the values in here in the meat of the chart are values, or they're the alpha E. That's the experiment-wise error rate as the number of contrast increases. And so this is saying that the experiment-wise error rate can be as large as, one contrast, 10%, as large as 19% for two contrast if alpha is 0.10, as large as 0.271, so a 27% error rate if alpha is 10%. And if you have 10 contrasts you're looking at, then the experiment-wise error rate is 65%. That is, the chance of making at least one error is 65%. Okay, so there's this compounding of error rates, and for the individual errors, individual tests, that shows up in this experiment-wise error rate. Okay, the same is true if you have an alpha of 0.05 or an alpha of 0.01. All right, and so anyway, this table gives you some insight into the fact that as this increases, as m increases, then alpha E is going to increase. And so we want a way to try to mitigate that. All right, we want a way to mitigate that. We want to control the experiment-wise error rate and not just the individual error rate. One approach is to use what's called the Bonferroni inequality. And in the Bonferroni inequality, it states that the overall error rate, alpha E, is less than or equal to the sum of the error rates for the m-test. So mathematically what that would mean is alpha E is less than or equal to m times alpha I. So if we want to guarantee that the chance of the experiment-wise error rate is at most alpha, well, what we could do is we could take alpha I and divide it by our original alpha I, or just alpha, and divide it by m, and then that would guarantee us a experiment-wise error rate of at most alpha I there. Okay, so I'm sorry, at most alpha. So for example, if we have 3 tests like we do here above, and we want an overall error rate of 0.05, we could take 0.05, divide that by 3, and do each individual test at 0.05 divided by 3, which is 0.016 repeating. If you did each individual test here at a 0.01666 and so forth significance level, then the overall significance level for the experiment of all 3 of these tests would be at most 0.05. Okay, that's what this Bonferroni approach is doing for us here. Now, the Bonferroni procedure is actually very conservative with respect to making a type 1 error, but this comes at the cost of losing power. So it's conservative. It's, you know, you're protecting yourself against a type 1 error, an experiment-wise. Let me make this clear, against making an experiment-wise type 1 error, but the power of your test, in particular the power of the individual test, is decreased as you adopt this Bonferroni approach. Okay. Now, the rest of the notes in this module deal with particular ways to run multiple comparisons. One approach, one of the more conservative approaches out there, is this Bonferroni approach. It can be done, but it's very conservative, and what that does for us is it gives us hypothesis tests that are not as powerful as they could be, and it gives us confidence intervals that are perhaps too wide, and so we want some other approaches here. And that's what these several methods here look at the issue of trying to control the type 1 error for the experiment, and also perhaps try to achieve an optimal power. But we're going to look, there's trade-offs between those two, and these methods that we're going to look at illustrate the trade-offs more or less. But we're going to have here several procedures, several multiple comparison procedures to look at multiple tests at a time. Now, this first procedure we're going to look at here is called Fisher's least significant difference. And the process is as follows. We perform an analysis of variance test to test the equality of several population means. If we reject that null hypothesis, then you remember that what that null hypothesis looks like. It's the F-test null hypothesis that mu1 is equal to mu2 is equal to, we have several population means. I think K is the number of means we generally look at. If we reject this null hypothesis, then we're going to continue on with this Fisher's LSD approach. Now, if there's insufficient evidence to reject H0 using the F-test, then we proceed no further. It's not recommended to use Fisher's LSD approach. And that kind of makes sense. If you don't have evidence to conclude that at least one of these is different than the others, then it's going to be hard to have an approach, or we need to be careful about finding an approach that identifies specific differences. And so the Fisher's LSD approach protects us against that. But if this null hypothesis is rejected, then we're going to proceed here to define the least significant difference to be the observed minimum between two sample means necessary to declare that the corresponding population means are different. Okay, in other words, to test say mu1 versus mu2, we're gonna look at y1 bar and y2 bar and check it versus this LSD quantity. Now the LSD quantity is given by this expression here, and it depends on the two means that you're comparing. But if you're comparing mu I and mu j, then you have a particular least significant difference, and it's a function of a t percentile. It's a function of the within sums of squares. That's actually it's the within mean square, MSW. That's what this S squared W is, and then the two sample sizes there. Okay, so we can get those readily for a given procedure, and then what we do is we compare the pairs of sample means in this way. We take the absolute difference and we ask the question, is it bigger than this LSD, the least significant difference? And if it is, then we're going to declare that those population means are different, or that those two sample means are statistically significant. All right. Now this approach, what it does is for each pairwise comparison of the population means, the probability of a type 1 error is fixed at a specific value of alpha. Okay. Now that's for each here. All right. That's for each pairwise comparison. So we need to be mindful of that. Now, a 100 times 1 minus alpha percent confidence interval for the difference of the population means is given by this expression. Basically, we just add and subtract Fisher's LSD there. Now, the thing about this confidence interval is that the confidence statement here is per interval. So it would be, we're 95% sure that the difference in the two population means is between some lower bound and some upper bound. That 95% would just apply to that particular interval and not all of the intervals. All right. Now this LSD procedure, perhaps you've seen this, it's analogous to a two-sample pooled t-test. And that's kind of what this looks like here, right? It kind of looks like the pooled the stuff from a pooled t-test, except what's different here is we use the pooled estimator of the population variance from all the samples. That's why we have this SW squared instead of the SP squared, and their associated degrees of freedom. To be clear here, LSD procedure often does a poor job of controlling the experiment-wise error rate. So as a result, while it's done, it's if a person is really interested in controlling the overall error rate or the experiment-wise error rate for several multiple comparisons, then the Fisher's LSD approach is probably not the first approach to look at. One of the first approaches to look at is this what's called Tukey's approach. Now, Tukey's W procedure here, there's a lot of words, a lot of text here to set up this procedure. But basically, the procedure says let's compare the largest sample mean and the smallest sample mean. And it does that through this statistic here. And with that statistic there, we have what's called Tukey's W procedure. Now it turns out this statistic does not follow a t-distribution. Rather, it follows this particular distribution called a studentized range distribution. And it follows a different distribution because the sample has been taken and a posteriori, after the fact, we have looked at the ordering of the sample means and then compared the largest and the smallest, and because of that the t-distribution would not apply. We don't have the independence that we need for the t-distribution. But the studentized range distribution, which was developed here, we can use it because that's what this follows, that new kind of, this for us a new distribution, the studentized range distribution. I'm not going to show you, we don't have a representation we're going to look at in the notes for the studentized range distribution, but just note that we can get from table T the relevant percentiles to use this distribution. Now, really I say that, but for us in this class, we're going to basically let a statistical package do most of the legwork in computing these multiple comparison procedures. All right, now so the process here is similar to Fisher's LSD process. What we're going to do is we're going to rank the K sample means, and we're going to declare that the population means are different if the absolute difference between the two sample means exceeds some W value. Before it was an LSD value, now it's a W value. If you look at the W value, it's given by this expression here, okay, which looks is similar to the expression for LSD, except a major difference is this Q instead of a T percentile, and the way the N is in the square root there. Now, what this approach does is it controls the overall error rate, or it controls the experiment-wise error rate if we were to test several population means. And any corresponding confidence interval that we have here, or the resulting confidence intervals, plural here, for all mu I minus mu j, the confidence statement is for all intervals. Okay, so this is a nice property of the Tukey's procedure, is that it controls the experiment-wise error rate in hypothesis testing, in multiple hypothesis tests, and it gives an overall confidence statement for all the intervals in a confidence interval situation. So that is a nice property of the Tukey's approach, is that it does control this overall error rate. Moving along to another multiple comparison procedure called Dunnett's procedure, and it's a particular procedure that is interested in making comparisons of mean values for a treatment to mean values out of control. So in particular, in many studies and experiments, the researchers will include a control for comparison purposes. And so for example, say if we're dealing with the additive problem, we have 3 additives that are fuel additives that are made to try to improve the fuel economy of a given car. Now suppose we had a 4th additive and it was the standard additive that was already on the market. It was the most popular additive that was already on the market, and we want to compare maybe the 3 new additives to that standard additive, that control there. So we would treat that as a control, and what we could do here is actually we're more or less interested in comparing the several means to the control mean. In other words, yi bar minus yc bar. Okay, and the Dunette procedure allows us to do that. Now, within this procedure we need equal sample sizes, although there's ways to allow for unequal sample sizes. And again, this procedure, to be clear, controls the experiment-wise type 1 error rate for those different comparisons. The process here is we specify for a specified error rate alpha E, we specify Dunette's D value, which is given by this formula here. It's a function of this D alpha, which is a critical value from a table for the Dunette's distribution. We're not going to reference that. Again, I'm going to let JMP or some statistical package compute these for you if you need them. But I just want you to recognize that, hey, Dunette's procedure, there's some mathematics involved behind it. And it is used to compare several population means to a control. And in particular, here are the 3 hypotheses that we could look at. We could look at a two-sided hypothesis. We're asking the question, is mu I different than the mean of the control? And so what you do here is you look at the absolute difference between the sample mean correspond to the ith population and the control sample mean, and ask, is that absolute difference, does it exceed the value D? And if it does, then we declare that mu I and mu C are statistically significant. We could have a right-sided alternative hypothesis. It would look like this there in the alternative, and we're going to declare the difference if we exceed this D value here. Now let me back up. If you were to use a table, these D values would be different. You'd have to reference a two-sided table or a one-sided table. But again, we're going to let JMP do that sort of thing for us. We could also have a left-sided alternative that would be as specified. Okay, Scheffé's S method. This is another multiple comparison procedure, but it's a little bit different. What it allows us to do is it allows one to test all imaginable linear contrast. The previous methods, Dunette, Tukey's, and Fisher's LSD, allows you to compare pairwise means. All right. Well, we know that linear contrast can be more general than pairwise means. The Scheffé's method allows you to compare as many linear contrasts as you want, and it still controls the experiment-wise error rate. Now, because of its ability to control so many or to test so many contrasts, this method is very conservative. All right, that is, it may miss out on a lot of significant differences that other procedures wouldn't, because it's so conservative. In the process here, again, it deals with linear contrast. So if we have this sort of linear contrast here, we could test to see if it's 0 or not, and we can actually do as many of these as we want. Here's the mathematics that we would develop if we were to do this sort of thing by hand. There's the mathematics we would develop to do this test, but we're not going to. And we again are going to just rely on JMP or some statistical package to compute these for us and to help us make decisions about these multiple comparisons. So here's kind of a final paragraph on multiple comparisons. We could teach a whole class on all the multiple comparison techniques that exist, their corresponding advantages and disadvantages, but you know, for our purposes, I just want to introduce you to the popular ones, what their respective advantages are, what their respective disadvantages are, and you be aware of that. Okay, but let's apply this, at least apply it in terms of we've got some output from JMP, and apply some of these methods. So again, the location example revisited. What would suppose we want to now test that all pairwise means. We want to do all pairwise comparisons rather. What do these hypotheses look like? So it's all pairwise comparisons. So let's think about what could we have. Well, H naught, we could look at mu1 is equal to mu2. The alternative would be that they're different. And we could compare mu1 to mu3. So its null and alternative would look like this. And notice I've got and in here. We could compare mu1 and mu4, and its null and alternative would be as follows. We could also compare mu2 and mu3. There's the hypotheses for that. We could compare mu2 and mu4. And then lastly here, the last comparison would be mu3 and mu4. Okay, so we actually have 6 pairwise comparisons here. 6 pairwise comparisons. In general, there's the number of combinations of choosing 2 out of 6 gives you the number of pairwise comparisons. We may say 6, choose 2 for that if you're thinking of a combinatorial or a counting idea from mathematics. We have 6, I may have misspoke. If I said 6, choose 2, I apologize. We have 4, choose 2, 4, choose 2. This is what I'm thinking about. 4, choose 2. Turns out to be 6. Okay, we cover that in the binomial distribution. But anyway, there's 6 pairwise comparisons here. Okay, now here's some output from JMP. Now you'll want to watch the JMP demonstration to see how you get this output, but here's some output from JMP for Fisher's LSD approach and Tukey's approach. Chaffee's approach is in there, but I'm just going to, for the notes here, I'm just going to reference the LSD approach and Tukey's approach. Now you can see what JMP has done for us. It went ahead and computed the least significant difference there, the t value there, and then it also computed the least significant, or the Tukey difference here of 2.7 that it needed there. Okay, so actually I misspoke. This is the t percentile. This is the q percentile from the Tukey's distribution. Those aren't the particular differences that we're looking at. You could reference those out of this table, but this is the t sub alpha over 2, and this is the q sub alpha over 2 there. Okay. Now in this table here, what it gives us, there's quite a bit of information in here, and I'm actually going to look at these first. This part right here, Fisher's LSD, this is called a connecting letters report. A connecting letters report. And what it does is it looks at all the pairwise comparisons through this kind of concise reporting scheme. And it orders, first, if you look here at the sample means, that's what it says here, the least squares mean. The sample mean for oceanfront is 210, the sample mean for bayfront is 204, and so forth. And these are ordered going within JMP. It's ordered them from going down largest to smallest. And so it's testing. Implicit within this representation is all of those 6 tests. And so what this tells us is that the levels that are not connected by the same letter are significantly different. And so the oceanfront mean and bayfront mean and oceanside mean, they're all connected by the same letter A. So we would not have evidence to conclude that the average selling price for oceanfront is different from the average selling price from bayfront. We would also not have significant evidence to conclude that oceanfront is different than oceanside. They're all connected by the same letter. But oceanfront and bayside are not connected by the same letter. And so that would indicate that there's a statistical difference between the average oceanfront selling price and the bayside selling front price. Okay. This is reading Fisher's LSD. Now again, Fisher's LSD is more powerful, but the cost is that the experiment-wise error rate is not controlled. Okay, so in other words, here we have 6 implicit comparisons that we're looking at. The type 1 error rate for the overall comparison is not 0.05, but it could be actually a little bit higher than that. All right, and we saw that by looking at a table earlier in this module. What's the stuff that is in here? You notice if we have 6 hypothesis tests, we could also have, say, 6 corresponding confidence intervals, and that's what is given in this part of the output. You can tell here where the interval information is red, then that denotes a statistical significance. Notice we're comparing oceanfront and bayside there, oceanfront and bayside. The difference in the sample means was 18.5, and the standard error of the difference is 6.35. The lower bound of the difference is 5.24, and the upper bound is 31.78. Okay, and because this confidence interval here does not contain 0, that's corresponding to you rejecting the hypothesis that the oceanfront mean is the same as the bayside mean, and we saw that in the connecting letters report as well. This information here is the same as what we have here. It's just the 2 categories are switched, and so that's why the signs are negative there. Okay, that's Fisher's LSD table. Tukey's HSD, it's called HSD, it stands for, from JMP, it stands for honestly significantly different. Okay, it controls the overall error rate. Tukey's does control the overall error rate of 0.05 as specified here. Now, if you look here, we can look at the connecting letters report. Again, we read it the same way as Fisher's LSD. This connecting letters report actually looks the same as the one over for the Fisher's LSD. That's not always the case, but in this particular instance, that turns out to be the same. And also here we have the respective confidence intervals using Tukey's approach. And so what we have here, if you want to focus on this kind of bottom triangle here, the information in there would give us 6 confidence intervals, and the confidence statement would be for all 6 intervals. So we would say we're 95% confident that the difference in the bayside and bayfront mean is between these 2 values and the difference in the oceanfront and bayfront mean is between these two values, and the difference in the oceanside and bayfront mean is between those two, and so forth. Okay, so that's an overall confidence statement in regards to these 6 different confidence intervals here. Whereas Fisher's approach, these intervals here were a per, the 95% was a per interval statement. All right. But the big takeaway is that we see here oceanfront and bayside are statistically significantly different. All right. We see that from our multiple comparison technique. So that's the big takeaway here, is that for this first question we have sufficient statistical evidence to conclude that, that mu4 is different than mu2. In particular, we could say that mu4 is bigger than mu2. When you look at the ordering of the sample means, that has to take place. That mu4 is bigger than mu2. In other words, the average, what is this, oceanfront selling price is greater than the average bayside selling price. Okay, the average bayside selling price. Now, that is the only significant difference we have. This is the only detected significant difference. Okay. All of the other comparisons, we would fail to reject the null hypothesis. So if I'm looking at these 6 hypothesis tests here, this is, what are we doing, mu4 and mu2? This is the only one that we would reject. All right, the others we would fail to reject. Okay, what we could do next then would be to compare the oceanfront and the bayside means via their confidence interval and interpret that. And so I'm going to make use of the Tukey's approach, the Tukey confidence interval, which controls the overall confidence level. The Tukey confidence interval on, we're going to look at mu4 minus mu2 is, I like to do the larger one minus the smaller one, just so we're in positive values, is 0.71 up to 36.3. Okay, and so let's see, right, where am I getting that? 0.71 up to 36.3, that's where that comes from. Now, if you recall, this is in thousands of dollars. That was the units for the data for the selling prices, in thousands of dollars. Okay, so what we would say here is, so we are 95% confident that the average oceanfront selling price is higher than the average bayside selling price by at least, now in the original units it was 0.71, but in terms of dollars, that would be $710. That would be the least difference in the averages, and the most would be, I'm going to move the decimal over for this one over 3 times, and that would be $36,300. Okay. What it would be, let's see, I missed some words in here, by at least $710 and at most $36,300. That's pretty important to include those. Now, is this wide? Yeah, that's a really wide interval. 710 to 36,300 on terms of average prices. In fact, if you look at the Fisher's interval, it's a little more narrow. It would be around 5,200 up to 31,700. So a little tighter interval there, a little more information in that. But if we want to control the overall confidence statements, then typically we do in a multiple comparison scenario, then we would go with this interval. So this interval is we see a significant difference. We can interpret this interval in this way. I do want to make it clear that this interval is wide. And you may ask, well, why is it so wide? Well, the thing that's driving it being so wide basically is we just have 6 data points per sample, and that's really a pretty small sample in order to do inference on means there. Okay, lastly here as a final statement, the overall analysis in the location example, we should temper this with the fact that if normality is a problem, then or constant variance is a problem, then maybe we should look at another technique. There's non-parametric techniques out there. Remember the Kruskal-Wallis approach is a technique that allows you to compare several population means, and there's an analog from that allows you to do multiple comparisons off of that approach. Your book discusses that. I'm not going to cover that in this class, in this module, but it does exist. Okay, so this wraps up multiple comparisons.